Okay, this is lesson 2 in our AQA A-Level Physics Fundamental Particles course, which I've called Fundamental Interactions. Now, a couple of things that we've got to talk through first before we actually get into the interactions, and one of those is mass in terms of energy. And of course, you know of E equals mc squared, and therefore this won't be any surprise to you. If we take the mass of an electron, mass of electron 9.11 times 10 to the minus 31 kilograms. Now, to convert the mass of an electron into the energy equivalent for that, we've clearly got to multiply by c squared. So, therefore, E is equal to mc squared, which is equal to 9.11 times 10 to the minus 31 times 3 times 10 to the 8 or squared. Okay, and that gives us an energy that's the equivalent of the mass of the electron of 8.2 times 10 to the minus 14 joules. So that's the energy that has got to be found in beta decay in order to make that electron before we can even think about giving it kinetic energy and firing out at close to the speed of light. That's the basic energy that's got to be part of the beta decay process to make the electron. But you'll be aware already that particle physicists don't really work in joules, and particle physicists work in electron volts, and therefore I've got to convert that into electron volts. And so in electron volts, that's 8.2 times 10 to the minus 14 divided by 1.6 times 10 to the minus 19. And that turns out to be 5.1 times 10 to the 5 eV. Now, that's a bit of an ugly number. If you press your engineering button on your calculator, then that'll come out at 511 times 10 to the 3. And if you press it again, you get 0.51 times 10 to the 6. And that's actually how physicists use that. The mass in terms of energy of an electron is half an MeV, half a mega electron volt, half a million electron volts. So 0.51 MeV, half a mega electron volt. Now, you can't really write mass as an energy, and so sometimes you see the mass of fundamental particles given in units of MeV per c squared, and that does indeed make it a mass, because mass is energy divided by the speed of light squared. Sometimes you'll even see it in giga-electron volts per c squared. Our course doesn't tend to bother with that bit, doesn't particularly like the per c squared bit, and so they don't refer to these things as masses. They refer to them as rest energies. So on your data sheet you have rest energies. And the rest bit comes from the fact that as particles start to go close to the speed of light, their fundamental mass changes as a consequence of special relativity. Their mass goes up as they get closer to the speed of light. And so when we're referring to rest energy, we're talking about the mass of the particle when it's sitting still, written as an energy. So rest energy is the term that's used in your course. So the rest energy of an electron, 0.511 MeV. The rest energy of the proton, 938 MeV. Rest energy of the neutrino is given in your data sheet as 0. Physicists today do believe it's got a value, it's just that value is tiny. Less than half an EV, sorry. So the electron, half an MeV, the neutrino, half an EV. So less than a millionth of the mass of an electron. So effectively 0, which is why your data sheet gives it as 0. And need to know is perhaps a bit strong, because you can always work it out from the values that are given to you on your data sheet, but it's a good idea to know that the ratio between the mass of an electron and the mass of a proton is of the order of protons 2,000 times heavier. It's it's a bit over 1800, isn't it? So if you've got that sort of roughly in your head, sometimes that's quite a useful thing to say, you know, in those 6-mark questions. If you can say, and the mass of the proton is about 2,000 times heavier than the electron, sometimes that'll get you a mark. Now, next problematic bit of physics to discuss is Heisenberg's uncertainty principle. You'll be glad to hear this is not on the course, so you don't have to reproduce any of this, but it's one of those things that everything else I'm going to say is a bit easier to understand if you've met Heisenberg's uncertainty principle. Plus, the idea in it is fun. Now, what this expression says is that uncertainty, now we've already come across the idea of uncertainty in our practicals, of position, where S represents its position in space. We could perhaps use S. And this is uncertainty momentum. Excuse me. And what Heisenberg's uncertainty principle says is that there are certain pairs of values, they're called conjugate pairs, where the uncertainty of the two of them multiplied together can't be less than h bar by 2. And we come across h bar, that's Planck's constant divided by 2 pi. So this is Planck's constant divided by 4 pi. So if I knew exactly, you understand from that knowing exactly is going to be problematic, but if I knew exactly where an electron was, then what Heisenberg's uncertainty principle says is I couldn't know anything about what its momentum was doing. Because if delta x drops to 0, then delta p, my uncertainty in the momentum, has to go to infinite in order to allow that inequality to be true. And that's quite a difficult idea. That's saying that we just don't know how it is things work. Oh, hang on, I'm going to have to pause. My cat's come to annoy me. He wants feeding, but I'm going to finish this first. Clear off your old cat. Now, the way Heisenberg thought about this, the way he wrote in his book that he wanted you to think about it, was he said, imagine a microscope, an optical microscope. So there you are. There's the barrel of my optical microscope with an eyepiece or a detector above. And he said, imagine that it's looking at a fundamental particle. Now, optical microscopes cannot look at fundamental particles. Fundamental particles are far too small to resolve with an optical microscope. But this is a thought experiment Heisenberg's doing here. He says, imagine looking at our fundamental particle with our optical microscope. He said, how do we actually look at something with an optical microscope? Well, what we do is we look at the photons that have scattered off of our fundamental particle. So photon hits our fundamental particle, goes up our microscope barrel, and is detected, so we know where the fundamental particle was. And what Heisenberg said to you is, of course, if we hit our fundamental particle with our photon, because our photon has a momentum, we talked about Compton scattering before, because our photon has a momentum, our fundamental particle is going to recoil after being hit by our photon. And that therefore we've changed the momentum. So in working out the position of our fundamental particle, we've changed its momentum. And so we've mucked up what's going on in terms of the uncertainties. We can't know one perfectly without the other. Now, it turns out that Heisenberg's interpretation is not correct. This is not a measurement problem. This isn't, we just got to design a better microscope. This is actually utterly fundamental to physics, that there are these pairs of quantities that we cannot know to greater uncertainties, smaller uncertainties than h bar by 2. This is what Heisenberg said about it, thinking about his microscope. And as I say, that's no longer thought to be the case. But this idea that the process of observation changes the physics is now what's known as the Copenhagen interpretation of quantum mechanics. That is, that when we actually make an observation, we collapse the wave function of our quantum mechanical system into whatever it is we've observed. Before we did the observation, it was doing all sorts of things, had all sorts of different possibilities, but all those possibilities collapse when we make an observation. So by making an observation, we change our relationship with nature. So our physics is producing a picture of our relationship with nature, rather than necessarily producing a picture of nature. And Heisenberg got there by thinking through his uncertainty principle. Now this is a different conjugate pair. This is the energy of an event multiplied by the uncertainty and the time of that event. And this one means quite a lot to me, as my sort of undergraduate degree involved a lot of what this picture is. This is what's called a Fourier transform. So if this is time on this axis here, then our time is getting transformed into its conjugate pair. Now for an electrical engineer, the conjugate pair will be frequency. But of course for us, that's energy, because E equals hf. So this is a representation of the way that those two conjugate via Fourier transforms. And Fourier transforms are just really lovely maths, and if you do any kind of technical degree, you'll almost certainly come across them, so at least you've heard of them. But the reason putting this slide up at all is that this relationship here places a fundamental limit on exchange interactions, but we haven't talked about what exchange interactions are yet. So let's get on to that. Quantum mechanical forces and the problem with action at a distance. Well, in medieval physics, and there was such a thing, most of the thinking was based on Aristotle's work. And Aristotle was, I think, about somewhere around 300 BC, 400 BC. He was Alexander the Great's tutor. And in medieval physics, action at a distance was not respectable. You were not allowed to imagine a force with no connection between the two things that are exerting forces on each other, even if it meant you had to sort of postulate the existence of angels pushing to explain what's going on. Action at a distance was just not respectable. And then action at a distance is made respectable by Newton, when Newton comes up with a really nice description of gravity. But of course his really nice description of gravity relies on gravity being an action at a distance, and he rather does away with all the, we don't have to worry about angels pushing it around anymore. We've got this bit of maths that describes it. And so lots of other physicists jumped on the bandwagon, and all sorts of different actions at a distance ended up being described. But today there aren't that many. There's electrostatics, there's electromagnetism, and there is gravity. And so we get rid of, in classical mechanics, we get rid of the problem of action at a distance. We don't get rid of the problem, but we sort of describe the problem in terms of fields, where the field is that object reaching out into space to influence other objects. So we'll do lots of that when we get on to fields at the end of year 12, beginning of year 13. But fields really don't do away with action at a distance. They don't do away with the problem. They just give it another name. And this same problem of what's creating the action at a distance it continues on when we go into quantum mechanics. And so quantum mechanics still have quantum mechanical fields, and it's found as a perturbation. Again, if you do physics, you do lots of perturbations. A perturbation upon quantum mechanical fields is virtual exchange. Now, I said that in the macroscopic world we've got gravity and we've got electrostatics and electromagnetism. On a fundamental level, we have 4 interactions. Don't really call them forces in your course, we call them interactions. I struggle with that a bit because I've always called them forces, so you'll find me making mistakes and calling them forces, but your mark schemes and things will only ever call them interactions, so you've got to get used to interactions. So in quantum mechanics there are 4 fundamental interactions. Interactions cause a change at a distance, and they do that by exchanging virtual particles. They do that by exchanging made-up particles. And each one of the 4 kinds of interaction has its own particular set of exchange particles or exchange bosons. So you've heard of boson, you've come across the term boson because you've all heard of the Higgs boson, which is part of the exchange system that gives everything mass. So fields have bosons, and our 4 fundamental interactions each have a set of bosons that you have to be able to name. So the electromagnetic interaction, now I said that when we do fields, we will talk about the electrostatic and we'll talk about the magnetic. A fundamental physicist doesn't really care because they're both to do with charge, and so as far as our fundamental physicist is concerned, they're one thing. And the interaction particle for the electromagnetic interaction, the exchange particle, is the photon. So the electromagnetic interaction exchanges virtual photons. For gravity, we have the graviton. That one's very controversial because quantum mechanical description of gravity with the graviton does not match up to the Einstein general relativity description of gravity. And that's probably physics' biggest embarrassment. Its 2 most successful theories never meet in the middle. And so trying to make quantum mechanical gravity be the same thing as general relativity gravity is sort of the fundamental goal of lots and lots of physicists, and is why things like string theory exist. Then we have the weak interaction. Now, you and I have already come across the weak interaction, because what does the weak interaction do? What change is it that the weak interaction causes? Well, the weak interaction causes one particle to turn into another. For example, a neutron becoming a proton in beta decay. So the weak interaction looks after beta decay. And the exchange bosons are the W+, the W-, and the Z0. And we'll do lots more about those. Well, the 2 W's anyway. The Z0 is just one. You've got to know its name and no more. We'll do much more about those later on in the course. And then the final one is the strong interaction. Now, the strong interaction, funnily enough, is very strong, and it sticks things together on an incredibly fundamental level. And so you've probably heard of quarks. The strong interaction is what sticks quarks together. And the exchange particle for the strong interaction is a gluon, and they do colour exchange. Yeah, I know, sounds daft. Now, you don't need to know anything more than the word gluon. There's sometimes a mark. If you're asked for an exchange particle, if you write gluon, you'll get the mark. Okay, let's have a look at how the electromagnetic interaction works. The electromagnetic interaction. Let's imagine we've got an electron. Imagine we've got another electron. Those 2 electrons are going to repel each other. How did they repel each other? Well, we imagine that they've exchanged a virtual photon. Gamma symbol is the symbol for any photon, not just a gamma photon. And if you have a look at this, it sort of makes sense. This one has fired out our photon. And it's clearly going to recoil, just the way a gun or a cannon recoils when it fires something out. This one has absorbed our photon, and in the process is also going to recoil. The demonstration that's sometimes done for that one is 2 people standing on top of skateboards on a nice smooth floor, throwing medicine balls backwards and forwards to each other. Well, the one who does the throwing, they'll recoil. The one who does the catching, they'll recoil. We get repulsion. So that works nicely. Problem is, imagine an electron and imagine a positron. Those two are opposite charges, so those two are going to attract. And how do we explain the attraction? We still say they exchanged a virtual photon. And that, of course, is much more problematic. The way I've seen it explained, it was in one of the A-level textbooks. It was also on hyperphysics, and hyperphysics is the website that every single physics teacher goes to double check they're not saying nonsense, because hyperphysics, I've never found hyperphysics to be wrong, so we all go to hyperphysics to just double check ourselves. The explanation that's offered is, imagine that our person on the skateboard for our electron here throws not a medicine ball but a boomerang. They throw it out that way. So therefore they recoil in that direction. But because it's a boomerang, it goes all the way around, gets caught by this person on this skateboard over here, and they recoil that way, and so we get attraction. I have no idea whether that helps you or not. So we have boomerangs spinning round to explain how it is the electromagnetic interaction, exchange of photons manages to make things attract. Do they help? Yeah. Right, you have to be able to draw these diagrams, which is why I've nicked a better looking one off the web. And you're supposed to know that the y-axis in these diagrams is representative of time, so time is flowing in that direction. And although it doesn't mark it on here, the x-axis is representative of space. Now I know space is 3D, so it's only a representation of space. It's just giving an indication of how our electrons are travelling through space. It's not really giving the three-dimensional space. It's just a representation of. And this is a particle interaction diagram. It looks almost exactly like a Feynman diagram, but it's not a Feynman diagram, and because we don't have antiparticles travelling backwards in time, which is very complicated and is what real Feynman diagrams do. So for our A-level, we use a cut-down version of the Feynman diagram called a particle interaction diagram. I'll probably talk about more of them when we get on to beta decay. Right, now, this thing up here should look familiar. It's the Heisenberg all over again, except I've changed a couple of things. This is energy rather than uncertainty in energy, and this is time rather than uncertainty in time. And the observant amongst you, yeah, I didn't think anybody would have done. The observant amongst you will notice that that is the other way around. So what I'm saying here is that for virtual particles, the energy and the duration of a virtual particle come in below or at the Heisenberg limit. So they're virtual because they never really exist in the real world, because they're existing on an energy and a time frame which is below that's allowed in the real world. This allows them to sort of get around normal physics. They can have things like negative energies. And as a consequence, we can get attraction. We don't just get repulsion, because they're going faster than the Heisenberg limit. Again, going back to hyperphysics, hyperphysics said that they're virtual if they're there and back again before the particle has noticed they've gone. And the particle can only notice they're gone with a value of the uncertainty principle limit. And so, provided our virtual particle is there and back again before our particle that did the emission has noticed, then it's a virtual particle. Now, this expression has some consequences. The main consequence is where a photon has no rest energy, no rest mass, the energy of a photon can be any value. The energy of a photon can go right down to 0, we know that that would mean the frequency would get incredibly long. It would be an incredibly long radio wave, but the energy of the photon can go down to down to nothing, which means the time, and still be able to satisfy this inequality, the time can go up to infinity. Now, given that the time is how long does it take for the particle to go, for the particle to be exchanged, if the time can go up to infinity, that means that the distances over which the electromagnetic interaction can take place are infinite. So because there's no lower limit on the energy of a photon, the electromagnetic interaction is infinite. And that's the same for gravitons as well. And what you have to imagine is that any charged particle is surrounded by this cloud of virtual photons. And this cloud is infinite in extent, but as soon as the time starts to go up, as soon as the distance starts to get large, the energy becomes almost nothing. So although theoretically they're infinite in extent, in reality the extent of our cloud of virtual photons is actually very tiny, because if it becomes large, this energy becomes too small to worry about. Essentially, forces drop off very fast with distance. Anyway, we have a cloud of virtual photons. Our cloud of virtual photons surround every charged particle, and where the two clouds intersect, we get virtual exchange. And virtual exchange results in attraction or repulsion. Oh dear, that's missing an N. There you go, got an N on now. Okay, the strong nuclear interaction. Imagine you're back in the 1930s. It's quite amazing. 1900, we didn't know what a photon was. 1930s, we're working out all these virtual exchanges and quantum mechanics, and basically physics has got as far as physics is going to get for quite a long time. Anyway, we need something to stick the nucleus together. It's not the strong force. Strong force comes a lot later. It's an aspect of the strong force called the strong nuclear interaction. And the nuclear bit, I always think it ought to be intranuclear. Intranuclear, meaning within the nucleus. So we have intra-island competitions, and they are within the island, and we have inter-island competitions, and that's between us and Guernsey. So it ought to be an intranuclear interaction or a internucleon interaction. I'm wittering now. We'll ignore all of that. Your course calls it the strong nuclear interaction. So this is the thing that physicists realised in the 1930s must be sticking the nucleus together. And a physicist called Yukawa, working in Japan, realises that this is going to be virtual exchange. And so says to himself, well, what properties must our exchange particles have? So they've got to stick the nucleus together, so they've got to strongly interact with the nucleus, seems obvious. Now, this one's slightly less obvious, but it's true for beta decay as well. The exchange is between both charged and uncharged particles. And so that requires three different versions of our exchange particle. We've got a positively charged one, a negatively charged one, and a neutral one. And as I said, that's true for the weak force. Beta decay. So he said there must be three. He said they only operate over the nucleus, so they're really short range. And if they're really short range, then the way to make them really short range is to give them a rest energy. It's the opposite argument to the one we made on the slide before. On the slide before, we said the photon has no rest energy, therefore E in our Heisenberg expression can drop to zero, and therefore T can go infinite. Well, here if we say our particle actually has a rest mass, if we say our particle actually has a mass, actually has a rest energy, then E can't drop to zero. E can only fall to some fixed value, which means our time cannot possibly go infinite. Our time can only rise up to what's set by that set value of energy, which means that the distance that the particles can exchange over and not have the particle that did the emission notice that they've gone becomes very short. So it's the opposite argument. If we've got a rest energy for our exchange particle, then we've got a very short range force. And because we can make an estimate of how long the nuclear interactive force is, we can make some predictions about the rest energy. And finally, all exchange particles are bosons, so they must be bosons. Now, Yukawa's analysis wasn't quite obvious. 4 years later, an Italian physicist called Wick, you wouldn't think Wick would be an Italian name, but an Italian physicist called Wick published an analysis that ended up with exactly the same result as Yukawa, and poor old Wick didn't realise that Yukawa had done it first because Yukawa published in Japanese and Wick didn't spoke English and Italian but didn't speak Japanese. So Wick doesn't get the credit for this. Yukawa does, even though actually Wick's analysis makes more sense to us. So this is that same Heisenberg expression again, except this time I've said equals. I've no longer got an inequality in there, just to allow us to work out a solid number. So if we want to know what the rest energy of our exchange particles are, we need to have some idea what the time of flight involved in the exchange is. Now, how can we get the time of flight? Well, of course, time is equal to distance over velocity. So what's the distance? What's d? Well, the minimum distance that could be involved here really is going to be the diameter of a nucleon, isn't it? Because if the two nucleons are pressed together to get from the centre of one to the centre of the next, it's got to cross the diameter. So nucleons are of the order of a femtometer. So protons and neutrons of the order of a femtometer across. So d, we're going to say, is roughly 1 femtometer. Now, a femtometer is 10 to the minus 15 meters. So we've got distance. What about velocity? Well, we can just postulate that they're going to go at the fastest possible velocity. They probably won't go at the fastest possible velocity, but let's assume they can go at the fastest possible velocity. And of course, that's the speed of light. So therefore, we can say that the time of flight for our virtual exchange particle is going to be 10 to the minus 15 divided by 3 times 10 to the 8. And you can reach for your calculator. That's going to work out at something like 3.3 times 10 to the minus 24 seconds. So there you go. We've got a time. Now, if we come back to this, then energy is equal to h over 4 pi t. And h is just Planck's constant, 6.63 times 10 to the minus 34 over 4 times pi times 3.3 times 10 to the minus 24 joules. And you bung that in your calculator, put it in your calculator, and you can come out with approximately 1.6 times 10 to the minus 11 joules. Now, you're also aware, because we've done it already, that particle physicists don't give energies in terms of joules, they give them in terms of electron volts, so we need to convert that into electron volts. So E in EV is equal to 1.6 times 10 to the minus 11 divided by 1.6 times 10 to the minus 19. And hopefully you don't need a calculator for that one. you can say that that's 1 times 10 to the 8 electron volts. And 1 times 10 to the 8 electron volts is equal to 100 MeV. So what Wick said, and he ended up with exactly the same conclusion as Yukawa, just Yukawa would use more difficult maths. What Wick said was that the exchange particles involved in sticking together the nucleus must be bosons of a mass somewhere in the region of 100 MeV. And 100 MeV, of course, is 200 times the mass of an electron. And so they're middleweight particles because they're somewhere in between the mass of the electron and the mass of the proton, which we know is 2,000 times bigger. And so they're middleweight particles, and so middle meson. And so these middleweight particles were known as mesons. They were thought to, and Yukawa and then Wick both predicted the existence of these mesons with a mass about 200 times the mass of an electron. And we'll come back to their discovery later on in the course. So, in summary for today, the particle mass can be expressed as a rest energy in MeV. Particle interactions use virtual exchange. And the exchange particle for the electromagnetic interaction is a virtual photon. Have to know that. Have to know that we can draw this stuff on a particle interaction diagram, and that has time on the y-axis and space on the x. I haven't emphasised, but it's true, exchange particles on such diagrams are drawn with a wiggle. You might notice I did draw them with a wiggle, but you might have just thought that's because photons wiggle. Then if the exchange particles have no rest energy, then the interactions range is infinite. And finally, because we're going to come back to this rather than because it's essential for your course, Yukawa proposed some middleweight bosons must exist in order to stick the nucleus together via the strong nuclear force, as your course calls it. Okay, that's it for today. These are the things that you have to know. Everything else is hopefully interesting, but not vital. This stuff, vital. See you.